In part 1 of the Unit 6 notes, we will be covering the introduction to bonding and structure of ionic compounds. A chemical bond is a strong force of attraction which holds atoms together in a molecule or crystal. There are 3 types of bonding which we will discuss. In ionic bonding, valence electrons are transferred. This results in a positive and negative ion which are then attracted to one another. In covalent bonding, pairs of valence electrons are shared between 2 atoms, which increases the stability of both. In metallic bonding, valence electrons are shared freely among all of the metal atoms within a large structure. Before we get into the specific types of bonds, we are going to learn how to draw Lewis dot diagrams. In these diagrams, valence electrons are shown as dots surrounding the atomic symbol. When creating a Lewis dot diagram, you should spread out your electrons before doubling them up. This will result in the maximum number of unpaired electrons, which will help when we eventually start to put these together within compounds. Atoms tend to gain, lose, or share valence electrons when forming bonds in order to have 8 valence electrons. By following this octet rule, atoms are able to achieve a noble gas configuration and additional stability. There are 2 elements that are an exception to this rule, and those are hydrogen and helium. For our first checkpoint, we are going to be looking at the number of valence electrons for each of these 3 atoms and drawing Lewis dot diagrams for them. Remember that in order to determine the number of valence electrons, you simply have to look at the group that the element is in on the periodic table. Magnesium is in group 2, therefore it's going to have 2 valence electrons. In order to draw a Lewis dot diagram, we are going to draw the symbol for magnesium, which is Mg, and then we're going to put the 2 valence electrons around it. You could put one on the left and one on the right. You could also put one of those 2 electrons in either the top or bottom position, which would be fine as well, as long as they are spread out so that the 2 electrons are not right next to each other. In number 2, we are trying to determine the number of valence electrons for sulfur. Sulfur is in group 6A or 16. That means it is going to have 6 valence electrons. For our Lewis dot diagram, we are going to have a sulfur atom, its symbol is S, and we're going to spread out our electrons. We have 1, 2, 3, 4, 5, 6 valence electrons around the sulfur. In our final example, we are now writing one out for argon. Argon has 8 valence electrons. We put our symbol for argon, which is Ar, 1, 2, 3, 4, 5, 6, 7, 8. So in our example with argon, we have 2 valence electrons on each of the sides for argon. When we have a total of 8 valence electrons, we know that it has a stable configuration. Next up, we are going to be discussing the structure of ionic compounds. When a metal, which has low electronegativity, reacts with a nonmetal with high electronegativity, electron transfer will occur. This process helps all the involved atoms to reach a stable octet, and the resulting positive and negative ions will be attracted to one another in an ionic bond. We can show this process using Lewis dot diagrams. It is important to note that the total number of electrons cannot change in a chemical reaction. That means that you can't add any extra dots within this process. You can only move around the dots that you already have. Electrons are going to be moved between the atoms and rearranged in order to form a stable octet. In the example that I have here on the left, we have a sodium atom which has 1 valence electron, and it is going to be transferring that atom over to the chlorine. That electron over to the chlorine. Now chlorine is going to have 8 valence electrons in its outer shell. It gets more stable. Now you might look at this and think that sodium no longer has any electrons shown, but that was only the previous valence shell. If you think about the Bohr model for sodium, you have 2 electrons in the first shell, 8 in the second, and then you have the 1 that was in the third. By getting rid of that 1 electron, sodium would have a stable valence shell underneath now with 8 electrons in it. In our example here on the right, we have an oxygen atom which needs 2 electrons in order to form a stable octet. When it forms a compound with sodium, it would need to bond to two different sodium atoms. Each one is able to donate one of its electrons to the oxygen to form a -2 charge. Our sodiums are going to go on either side of the oxygen. The reason why we draw it this way is because the two positive charges would not want to be next to each other within the structure. So we represent that within the Lewis dot diagram by having them on opposing sides, since both of them would be attracted to the negative charge in the middle. In our final example here, we have a magnesium atom which is going to be transferring electrons to chlorine. Each chlorine can only accept one electron because it already has 7 in its last shell. So one electron will go to the chlorine on the left, and one electron to the chlorine on the right. This results in a magnesium with a +2 charge, and two chlorines, which each have a -1 charge. On this slide, we have some pictures from the Dogs Teaching Chemistry video, which will be assigned in class. In this picture, each one of the dogs is representing an atom. The dog on the left is chlorine, the dog on the right is sodium. Chlorine is a very electronegative element, so in this example, the dog on the left really wants the toy that the dog on the right has. That toy is transferred over to the dog on the left, and the result are two ions, an anion being our negative charge and a cation representing our positive charge. For our next checkpoint question, we are going to be drawing Lewis dot diagrams for each of these ionic compounds. For our first example, we have lithium, which is in group 1, so it has 1 valence electron. Fluorine is in group 7, so it has 7 valence electrons. Electrons will always be transferred from the metal to the nonmetal. So this dot is going to go over to the fluorine, and now I'm going to have a lithium with a +1 charge, and the fluorine with a -1 charge. We have 1, 2, 3, 4, 5, 6, 7 valence electrons from the original atom, and then the new valence electron which comes in from lithium. We draw brackets around each of these ions to show that they are two separately charged particles and that the electrons are not shared in the middle. Now, if you are writing this on your paper or if you are trying to fill it within on Cami, I suggest that you try to use different colors to color code like I did in the previous example. Maybe use blue for some of the dots and then red for others, just so that you can more easily keep track of where the electrons are going to and from. If you're unable to do that with colors, you can also use different symbols. So maybe you use an X for this electron so that we can see that this electron right here came from another atom. In our next example, we have strontium, which is going to be giving up its 2 valence electrons that it currently has. And it's going to be giving them up to the bromine atoms. Bromine starts with 7 valence electrons. So we're going to put one of these bromines on either side. And for consistency, I'll actually turn these dots into X's so that we can track their movement as we go through this problem. These electrons are going to be transferred over to the bromine. Now what I'm doing here, this is essentially like showing your work in a math problem. This isn't really the final product. In the end, I'm going to have an SR which now has a +2 charge because it has given up 2 electrons. I'm going to redraw my bromine here with its original 7 valence electrons, and now it has the X, which it took from the strontium. Overall, that's a -1 charge. On the right side, I'm going to have my other bromine with the 1 electron that came from strontium. So important for these ionic Lewis dot diagrams, you should end with brackets so you can see each one separated from one another, and of course the charges. The charges should always add up to 0 since you would have a neutral compound in the end. In our final example, we have K2O, so we're going to have 2 potassiums and 1 oxygen. The oxygen in the middle is going to have 6 valence electrons. And then our potassium, each one is going to have 1 valence electron. We'll put the X's on the potassium this time. So these electrons are going to be transferred over to the oxygen. That's going to end up with a -2 charge because it gained 2 electrons. Potassium is now going to form a +1 charge. For our next question, we are asked how you could determine that these three compounds contain ionic bonds by using the formulas. That's just this part here. Now, we had mentioned earlier that in an ionic bond, you are going to have metals and nonmetals, or at the very least, electronegative and high electronegative and low electronegative numbers. So the best answer here, we could say that we are going to have a combination of metals and nonmetals bonded together. Or you can compare the electronegativities. For the examples that I'll be giving you in class, it'll probably be easiest to just look to see if you have a metal and a nonmetal to determine if it is ionic or not. The term isoelectronic refers to an atom and an ion of a different atom, or two different ions, that have the same electron configuration. If we consider the lithium and fluorine example from the previous slide, lithium lost an electron and now has a similar configuration to helium. Fluorine gained an electron and now has a similar configuration to neon. Helium and neon are both noble gases, which is why both atoms now have the additional stability. For our next checkpoint, we are going to draw a Bohr model for F-1 and neon in order to prove that they are isoelectronic. If we have regular fluorine, we are going to have 9 protons, 10 neutrons, and our shells would be 2 and then 7. But since this is going to be fluorine -1, we're gaining an extra electron. That's going to fill into the final shell. For our neon atom, we are starting with 10 protons, 10 neutrons, and 10 electrons, which will fit into the first 2 shells as well. So since these have the same exact number of electrons in the same shells, we can say that they are isoelectronic. When creating a Lewis dot diagram for ionic compounds, we use the formula unit of the compound. A formula unit represents the simplest ratio of ions involved, and in a formula this is shown using the subscripts. So in our example with sodium and chlorine, there is 1 sodium for every 1 chlorine. In reality, single ions do not group together in such a way. Within an ionic structure, every positively charged particle will be attracted to all of the negatively charged particles in a repeating pattern. The ratio of positive to negative ions is based on the number of electrons transferred. So here you can see an example of what an ionic structure would look like if you were able to zoom in. You would have a positive sodium, which is completely surrounded by negative chlorines. And for each one of your negative chlorines, they are completely surrounded by positive sodiums. The strong attraction between ions due to the difference in charge and the rigid crystal lattice structure leads to some common properties found in ionic compounds. That concludes part 1 of the Unit 6 notes. When we come back in part 2, we will be looking at the properties of ionic compounds.